So welcome to the video. Today we're going to take a look at how to do a paired t-test on version 31 of SPSS. So we're typically going to use this test when we have a continuous dependent variable and when we have a within participants or within subjects independent categorical variable comprised of two levels. So for this example, we are going to imagine that we are interested in the number of crime incidents committed before and after installing lighting within a neighborhood. So in this A column, we have the number of crime incidents before installing lighting, and in this B column, we have the number of incidents after installing lighting. So the paired t-test is going to tell us, is there a significant difference in the number of crime incidents before and after installing the lighting? So let's take a look at how to put these data into SPSS. So we will start off by going down to variable view, and then we'll go to this name column, and we're going to put one of the levels of the independent variable into this top cell. So let's just call this before. So that's going to represent before lighting. And then in the cell below, let's put after. So that means after lighting. Then we'll go to this measures column, and we'll say that we have scale data, which is another way of saying that we have continuous data, essentially. So let's go down to data view, and we can see that we have before and after at the top of these two columns. So then we can go back to this Excel spreadsheet, and then I'm going to select the top left cell in that column, and then I'll go down to the bottom right cell, and whilst holding shift I'll select that cell. Then I'll go to Command or Control C to copy the data. Then I'll go back to SPSS, and I'll select the top left cell, and I'll click Command or Control V to paste those data in. If that doesn't work, which is sometimes the case, you can go up to edit and then down to paste, and that should work. So one of the assumptions of the paired t-test is that the differences between the two time points are normally distributed. So to check this assumption, we actually have to create an additional variable, and we can do this by going up to transform and then to compute variable. And then we can transfer before over here using this button, and then we can go to minus, and then we can transfer after by using this as well. And then we can give a name to this new column or variable that we're going to create. So I'm going to call that difference, and then I'll go to OK. And then we can see that we have this new column here. And if we look at this first row, we can see that we have a 14 here and an 8 here. And 14 minus 8 is 6. And then we have the same sort of thing all the way down through this column. So that's how we create that variable. Now let's take a look at how we can check whether the values in this column are normally distributed. So to do this, we can go to Analyze, then we can go to Descriptive Statistics, then over to Explore, then we can transfer this difference variable to this dependent list, then we can go to Plots, and we can untick stem and leaf, we can tick histogram, we can tick normality plots the tests, and then we can go to Continue and then to OK. And then we can take a look at this tests of normality table. So we actually have two tests within this table. So we have the Shapiro-Wilk test on the right, and we have this Kolmogorov-Smirnov test on the left. And we typically use the one on the left when we have more than 50 rows or participants in this case. And we typically use the one on the right when we have fewer than 50 rows or participants in this case. So here we have 30 rows or participants. So we're going to focus on the Shapiro-Wilk test. And what we want to see is that the value in the SIG column is above 0.05. So in this case, it's way above 0.05 because it is 0.914. So this supports the assumption that those difference values are normally distributed. And if we scroll down slightly, we can see that we have this histogram. And when you're looking at these histograms and you're assessing whether the data are normally distributed, you want to see that you have a symmetrical bell-shaped distribution. Here, it looks quite good. It doesn't look perfect, but it's more or less consistent with the statistic here, which suggests that the data are normally distributed. If you find that your data are not normally distributed, you might consider doing a Wilcoxon signed ranked test instead, as this is the non-parametric equivalent of the paired t-test, and it doesn't make this assumption about normality. So having checked out, we can go up to Analyze, and then down to Compare Means and Proportions, and then over to Paired Samples t-test, and then we can transfer before and after. So I'm just going to select those both. We can transfer them over here using this arrow, and then we can go to OK to run the analysis. And I'm firstly just going to look at these statistics in the Paired Sample Statistics table, And we can see that we have a mean of about 18 before the installation of the lights, and we have a mean of about 13 after the installation of the lights. So it looks like there were fewer crime incidents after installing the lights compared to before, but we don't yet know whether this difference was statistically significant. And to determine this, we need to look at this paired samples test table. And specifically, we're going to focus on the significance part of it. And we can see that we have two p-values here, and which of these columns you look at is determined by whether you had a one-sided directional hypothesis or a two-sided non-directional hypothesis. So in this case, a one-sided directional hypothesis would be something like it was hypothesized that there would be significantly fewer crime incidents after light installation compared to before, whereas a non-directional or two-sided hypothesis would be something like it was hypothesized that there would be a significant difference between before and after with respect to the number of crime incidents. So the one-sided hypothesis is more specific than the two-sided hypothesis. So let's imagine that we had a one-sided hypothesis, and we can see that this sig value here is less than 0.001, and as that is less than 0.05, it indicates that there was a significant difference in the number of crime incidents before and after installing the lights. So that's essentially how we interpret the results, but let's now take a look at how we can report them. So I have an example here, and I've said that the paired t-test was conducted to compare the number of crime incidents before and after light installation. And I've said that a Shapiro-Wilk test indicated that the differences between the time points were normally distributed, and then I've inserted these stats here. So we have a W statistic of 0.98, and if we go back to the outputs and we scroll up to this tests of normality table, we can see that we have the statistic column here, and we have a value of 0.984. So I've just rounded that to 2 decimal places. We have a degrees of freedom value of 30, and we have a sig or p-value of 0.914, and we have that degrees of freedom value here, and we have that p-value here. Next, I've said that there were significantly more crime incidents before light installation compared to after, and I've inserted some means and standard deviations. So before light installation, we have a mean of 18.20 crime incidents. So that is coming from this paired sample statistics table. Here's the before row, here's the mean column where we have 18.20, and the standard deviation is 4.86 if we round that to 2 decimal places, and that's what we have here. And then I've just reported the same statistics for after light installation, which are coming from here and from here. Next we have the t-test itself. So we've said that t equals 6.89, and that's coming from this paired samples test table, and we have this t column here where we have a value of 6.894. So I've just rounded that to 2 decimal places. We have a degrees of freedom value of 29, and we have a p-value of less than 0.001, and that's what we have here. So here's the degrees of freedom value, and here's the p or sig value. Finally, I've said that the effect size was large, and I've reported this Cohen's d value of 1.26. So that is coming from this paired samples effect sizes table, and from this Cohen's d row and point estimate column, where we have a value of 1.26 if we round this to 2 decimal places. And I've described this as large, and that's based on these criteria here. So I've said that values between 0 and 0.2 typically represent very small effects. Those between 0.2 and 0.5 represent small effects. Those between 0.5 and 0.8 represent medium effects, and those above 0.8 represent large effects. And I've mentioned here that these same thresholds apply if you have a negative Cohen's d value as well. So a value between negative 0.5 and negative 0.8, for example, would also represent a medium effect, just like a value between 0.5 and 0.8 would represent a medium effect. So here we have a value of 1.26, and as this is above 0.8, I've described that as a large effect. So that's essentially it for the paired samples t-test on version 31 of SPSS. I hope that was helpful. If you have any questions, just let me know in the comments, and I'll try to get back to you. Thank you very much for watching, and I'll see you next time.